almost.
Okay.
All right.
We're good.
Hi, we're the IREE team. We joined the MLIR effort at Google before it went public last year, and have been working on various things. The thing we're going to present today is our work to create an end-to-end compilation runtime stack for Vulkan-based computation, or things that are shaped that way. And I'm going to turn it over to Ben Vanek, who this was largely his brainchild. So, please.
Yeah, so it was mentioned that end-to-end means many different things to many different people. And with this project, now that we've been working on it for about a year, it means many different things to us too. So this is just one example of an end-to-end flow, where specifically what I'm going to be talking about is how we started modeling scheduling of workloads in MLIR, the kind of dialects we used in doing that, what we found as we were going through that process, and why we think it's interesting. So hopefully what you'll get from this is some more inspiration for how MLIR can be used to model these kind of operations that are traditionally left kind of out of the big picture. So IREE is backronymed into Intermediate Representation Execution Environment. And basically what it is at a very high level is a set of compiler tools built on MLIR to get us to the point where we can start reasoning about scheduling logic for efficiently scheduling edge devices. That's kind of our team's mission is to make mobile, embedded, all those kind of devices really scream. And for our kind of end-to-end flow, what that means is not just creating another compiler pass and throwing it in the compiler, but really thinking about this holistically from the input modeling language, whether that's TensorFlow or JAX or PyTorch, through the compilation stack based on MLIR and to runtime. The idea being that you should be able to take a model directly from the source and execute it without kind of any missing steps. And what we do in the compiler is kind of baseline on the XLA HLO dialect as represented in MLIR as just an example of a nice, like well-factored small opset of dense math. And so kind of from the source model to the compiler side, there's things like the TensorFlow bridge for lowering TensorFlow graphs to the HLO ops. As well as other projects like PyTorch XLA can be used. And really, we're not tied to XLA specifically, it's just a good dialect for representing that. And as work continues in core for kind of developing linear algebra as a core dialect, we're looking to switch to that. Once we have this HLO dialect, which represents dense math basically on tensors, what we're really trying to do is identify the concurrency scopes that we can see within the IR. This is something that normally is kind of done as a fusion step, kind of identifying very, very carefully picked sets of ops into fused elements. But what we're really looking for here is data flow. We don't actually care what the ops are specifically, whether something's an add or a mul or a dot. What we're really looking is how do the tensors flow through the program, and how does that interact with things like control flow and stateful variables. And I'll get into that as we talk about some of the dialects we're using to represent that. Once we've done that, we need to actually start reasoning about how we execute these things. And for that, we're using MLIR as kind of a way to, once we find the things we actually want to execute, invoke MLIR to then get us to the various backends we want to execute on. And you can think of this as kind of like combining both a compiler and a linker and a kind of step for building multi-architecture fat binaries and things like that, which is kind of fun. So it's kind of recursive. We invoke MLIR to build our stuff and then invoke MLIR within ourselves to then build the other things. So this means as other backends are supported by the MLIR ecosystem, for going to LVMIR, for going to SpearV, for going to PTX, we can take advantage of that because we're just basically asking for MLIR to do its thing. And then finally, as the compiler step, we kind of wrap this all up in a nice little module that looks a lot like a shared object. and kind of throw that over the wall to the runtime. And the real goal here was to kind of get a very strong separation between the compiler side and what we actually produce in this shared object-like module, and the runtime side, which, as opposed to kind of traditional ML runtimes as you'd see them, that are very aware of kind of the ML-ness, right? They might have a first level, primary tensor representation. They might know about ops, whatever ops are, and op registrations and things like that. But our runtime here really is just a shared object loader for loading these modules that we've compiled. A hardware abstraction layer that kind of mimics very closely the Vulkan API, but can kind of have any number of backends. And then optionally a little interpreter that lets us load these modules from a non-compiled form. So that means if you're deploying to a device where you want to be able to download a binary and run it, but you don't have access to downloading executable code, you can still do that. So basically flexible deployment scenarios, flexible target devices via the hardware abstraction layer, and kind of flexible composition of these compiled modules via the dynamic loader. And the kind of real goal as we're thinking about what we're doing in the compiler is really exploiting kind of as much as we can the latency hiding ability of the hardware we're targeting, which usually means GPUs, but can mean edge TPUs as well, and even CPUs in a lot of cases. What we want to do, and kind of what anyone who's targeting these devices who wants to minimize power consumption, minimize thermals, minimize interruption to the user if this is an interactive device and you're running multiple things, is build as deep of pipelines as possible, communicate those pipelines to the lower level system, whether that's the GPU's driver, which then is going to a command processor or a big shared thread pool, and kind of allow that to do the final scheduling. And the kind of thing we noticed as we're targeting these edge workloads and such on mobile is that most of our workloads are very much underutilizing the actual hardware. We might have a couple big gems, but most of the models are batch size 1. For example, if you're translating a sentence on a phone, you usually only need to translate a couple of them. You're not, as you would in training, translating 10,000 of them at once. And so usually when you kind of are not able to build these pipelines, you can still get decent utilization just by kind of brute forcing your batch size, just keep increasing the batch size until your utilization number is good. But that doesn't work in these scenarios where you might be trying to transcribe speech to text for a single speaker. So what we're really focused on here are these workloads, the workloads that you can't brute force. Doesn't mean it's the right tool for all jobs. If you do, get to build big batches, then there might be other things, but this is really focused on this workload. And kind of the key takeaway for all of this is that co-optimizing scheduling and execution is really, really powerful. And it's something that traditionally in systems, as they've been thinking about kind of the ML workloads, kind of punt on and leave to the runtime. So, this is kind of like, systems that might represent a graph or little snippets, kind of shoving those to runtime and making the runtime deal with effectively scheduling those. What we're kind of looking to do here in MLAR is raise the level that we're working at such that we're able to reason about the scheduling as we're able to reason about the execution and make cross-cutting optimizations across those. And one of the things we found that MLAR lets us do is represent all of these in the same IR at the same time and take those things that are traditionally runtime related and move them into the compiler now in a way that doesn't mean building yet another compiler stack. And this is not a novel insight. This is kind of how things are traditionally done for things like GPUs. You really are splitting the scheduling from the execution, and this manifests itself like all the way through the stack. The scheduling code might be written in C or C++, talking to Vulkan or OpenCL or any of the system APIs, fibers, thread pools. And then the actual things you're executing will be written in a completely different language. That might be HLSL or GLSL for shaders on the GPU, or compiled kernels and pre-built libraries. But they usually are very separate. And so what we're really trying to do here is, whereas most of the compiler technology has been focused on the execution side and how to efficiently, process nested loops of various dense math, we're really starting to think about what if we also look at that scheduling half as well. And now effectively the same thing, but with rectangles. What we're really trying to do is build a DAG, a dependency graph of both execution and data flow, and then split that into the actual DAG of execution and data flow from the execution itself, allowing the scheduling to happen independently from the execution. And this is how you get the latency hiding effects, is you communicate the schedule to your underlying system, whether that's, again, a executor thread pool or the GPU driver or whatever, and let it consume as greedily as it can the work that you provided. To do this effectively, though, you have to be able to identify what is actually able to run concurrently and be able to communicate all that dependency information with a high fidelity. You don't want to introduce false barriers here that end up with bubbles in your pipeline. You don't want to introduce like post round trips, kind of, the same concepts that appear in networking and databases and everything for building transactions and submitting, not doing blocking round trips on TCP sockets is the same kind of stuff that comes into play here. And that's basically what we're trying to do. You can think of these data flow DAGs as kind of transactional units that we're able to submit to the lower levels of the system without any intervention in between them. And what is commonly focused on the execution side is kind of the memory hierarchy. You're talking about your registers and L1 caches and things like that, and that's all super important to those execution parts. But something that's often kind of looked over is the fact that that same kind of hierarchy exists at a scheduling level, kind of at many different levels of representation, whether this is talking about user to kernel mode switches as you're actually talking to different driver APIs, or cross-process hops as you're doing, secure, isolated, out of process work, up to the logic in your application that's kind of reasoning about how you want to schedule these workloads. And if you think about all the work that's gone into dealing with that on the execution side for the memory hierarchy, what we're really looking to do here is start to reason about the scheduling hierarchy in a very similar way. And the kind of real thing that comes out, again, with the workloads that we're looking at of very small batches and usually very interactive, is the system has the system as a whole, the ecosystem has basically built itself to hide latency. And there's some software out there that's really good at making use of this, partially because they were co-developed, and that's games. And so these are just some fun things and some fun talks from particularly a talk at GDC a couple of years ago about brain graphs. But the kind of fun thing, if you go look at how game engines do their scheduling to effectively utilize the GPUs and the CPUs, they build giant task graphs with dependencies between all the items. Usually these are done in kind of a somewhat declarative way. And they use this to great benefit to be able to get advanced allocation, kind of flexible scheduling in terms of, I don't necessarily care when this happens, just so long as it happens in this particular order. Or I don't care what the state of the memory is in the middle of my operation. I only care that the output is valid. And so these same kind of things that have been happening in games for a while and kind of have co-developed with the modern scheduling APIs for GPUs, these graphs look a lot similar, or a lot like a graph viz that you'd look at of, a ML graph. And that's kind of the again, not so novel key insight here, is that if we can start to do some of the things that the game engines have been doing to schedule these workloads, and do that in a way that does not require a whole bunch of hand coding of C++ and kind of crazy reverse engineering of the semantics, we can get some better things. And the allocation in particular is one here that we're spending a lot of time on, because the allocation within any executable you're actually running is usually fairly fairly well deterministic. Like that's, you know, a particular invocation on a GPU might use some certain number of registers and some shared memory. But when you're thinking about the whole system here, especially if you're thinking about building deep pipelines, you really need to start reasoning about how much memory you're allocating, when that memory is pinned, how long it's pinned, and again, try not to introduce any false dependencies. And so this screenshot here is an example from the frame graph talk in the previous slide, that their whole system was basically designed to identify those places where they had small transient buffers and collapse them without sacrificing concurrency. And that's basically what we're looking to do. Again, just as you would think about this in the memory hierarchy and like very carefully reasoning about, you know, your inner loop stuff should all stay in registers and it's fine if the stuff on the outer loop goes to the heap. We can think about the same thing for the scheduling hierarchy. And one of the kind of important things here is normally this kind of work is done at runtime, inferred based on the usage, whereas by modeling this in the IR itself, particularly across the boundary between scheduling and execution, we can do a lot of clever things and things that don't have large runtime impacts. And kind of for people who aren't familiar, this is just kind of like the things you do when you're handwriting code, say in C++ to schedule against one of these modern APIs, that you really have to keep in mind. And I'll kind of draw the line between this and what we're doing when I get to the dialects. But when you're talking to these APIs, you really are just building command buffers to submit for deferred execution. There's no kind of implicit barriers that are happening between your dispatches. And the code that you write to schedule these things is often running in time, very separate from when the execution will run. And so like here, for example, I'm recording a command buffer, and if I don't include a barrier there, there's no implicit barrier to protect me from stomping over my own memory. And so it's very critical to getting good utilization to make sure that you are inserting the barrier, well, for correctness, you're inserting the barriers where you absolutely need them, but you're not inserting barriers where you don't, because that just kind of flushes the system and kills you. We can also do things like, as you're recording these command buffers for deferred execution, you can embed a lot of the parameters that you're using right in the command buffers. So you don't have to think of, I have one global pinned buffer that has my arguments in it, and then now I'm going to dispatch and it's going to use that. You can use ring buffers, like ring buffers are kind of the whole primitive there, so that again, you're not creating false dependencies between your work. Things like dynamic shapes are kind of, you know, just natural in this system. So that's kind of nice. Like you can think about the shapes that you're working with separately from the actual execution, which means you can perform allocations and layout planning ahead of time when you're recording command buffers, as opposed to needing to do it in the actual execution. There's also a lot of cases where the kind of things you're deciding to execute are based on constants or you know, parameters to the model that are kind of known at startup time. And that's like in this example, the little grayscale flag. I'm not having to wait until the point that I execute to decide which of these next pipelines I should execute. I'm able to record that directly into the command buffer. And the ability to do that, to kind of conditionally encode different commands, is really important. And then finally, none of this was actually executing until I submit. And there's a whole bunch of different synchronization primitives that you can use to kind of order these things, such that if you have multiple command buffers, you can sequence those and kind of together. You can sequence submissions together. You can sequence the commands together. Again, it kind of gets back to that full hierarchy. And I've been talking a lot about Vulkan because that's kind of what, as a good distilled model for a kind of hardware independent API, we've kind of decided to model our stuff after, which means that when we're targeting Vulkan, we basically, our runtime is just a one-to-one calling down to Vulkan calls. But this applies for all other GPU APIs, modern GPU APIs, as well as kind of traditional CPU scheduling. They all kind of have parallels in here. And so really, when we're talking about kind of end-to-end automation at this level for the scheduling, what we're talking about is all of those things that you have to keep in mind if you were to handwrite this stuff. We want to bring those into the compiler and do that for you, basically. So the way that we do that is we've created a set of dialects in MLIR that we lower through, and at each one of those stages, we kind of very carefully are picking our representation to allow us to kind of extract as much as we can in terms of the optimization space at those different levels. Again, these kind of things in terms of the exact scheduling of your operations, the exact calls that you're calling into in your lower level APIs are usually done on the runtime side. It'll be kind of semantics for doing lazy tensor allocation, and I don't know. Normally they just kind of guess. And so what we're doing here is we're saying, as our input format to our compiler phases, we kind of need well-defined tensor value semantics, and this lets us utilize the SSA form IR that we have in MLIR, and all of the kind of normal folding and operations that are really easy to do with that. So this is, if you start with a TensorFlow graph, you convert it first to XLA HLO, and then you're at the entry to us. And so any of the potential inputs you have, as long as they can canonicalize through the MLIR conversion framework into this form, is now something our compiler can accept, which is super powerful. We no longer have to tie the optimizations that we're performing, which are relatively agnostic to what an op is or how an op is defined or the shape function used to determine the output shape. All of that happens above us and kind of by other parts of the MLIR ecosystem. So this is kind of getting to the point where now this whole project sounds really big, but really what we're able to do here is focus on the one thing that we really care about, which is the scheduling, and leverage the MLIR ecosystem to kind of take care of the rest. Once we have this kind of baseline input, and though again today it's XLA HLO, but any linear algebra like thing that can represent tensors as values and kind of allows us to get real shape information is acceptable. The first thing we do is we lower that to a dialect, the flow dialect, that's focused on data flow and execution flow modeling. So in this dialect, everything is still tensors, SSA values that are kind of flowing through the system. But it allows us to start detecting when concurrency is available and start to piece together parts of the system that later will want to do things like put into the same command buffer or introduce barriers and things like that. Once we've kind of done this work to model what is the scheduling related code from the code we actually want to execute, we lower to our hardware abstraction layer dialect, which is pretty much one-to-one with our C++ HAL implementation intentionally. But the reason we're able to represent this in IR or the reason we want to represent this in IR is that there's a lot of the kind of optimizations that are normally done at runtime, caching systems, LRUs, et cetera, for kind of the traditional stuff drivers like OpenGL tried to do, like guess that, oh, you're asking for this buffer, and so I'll just happen to use the buffer I already used, and et cetera. But we can do all of that at compile time, and the kind of optimizations we can do in terms of threading these things through and detecting redundant barriers or barriers that might be introducing false dependencies is now something we're doing with a really nice IR, a really nice transformation system. And can do it consistently across both the scheduling and execution side. If at this point, once we're down at this level, we decide that we made a mistake higher up the stack in terms of how we put pieces together, we still have a chance to fix it. Again, this is kind of different than if you were waiting till runtime and you've just been thrown something over the wall that you have to make fast. We can actually work on making it fast here. And the other thing we know at this point is our compilation targets. So this might be simple. It might be we're compiling just for Vulkan and SPIR-V, or it might be a kind of heterogeneous build where we want to, at runtime, be able to decide if we want to run Vulkan and SPIR-V, or ARM on the CPU with the CPU scheduler. And we can invoke MLIR to compile us for those different backends and embed them in here. The hardware abstraction layer, because it's just dealing with the scheduling of the work, is agnostic to which of those backends is actually used, which is really nice. We have kind of one scheduling model that's really trying to extract the most concurrency out of the system as possible, and how that actually executes now is left to other parts of the MLIR ecosystem. And then finally, we kind of model a virtual machine in the IR, and the key thing that we kind of model here is a very restricted subset of what you can do, and that kind of gives us some benefits as we start to think about like remote execution of these. And in our case, the remote execution means like executing in a persistent kernel on the GPU, or executing on a sidecar, ARM M4 processor sitting right next to an edge TPU. And the other thing it lets us do is natively support things like deferred execution for concurrency. So this is the case of it's manifested as coroutines, but if you're doing a whole bunch of work against one of these models, so you're invoking a whole bunch of the methods and you're building up a very deep pipeline, you want as much work as possible coming into the system, and one of the ways you can do that is by allowing those invocations to continue stacking. And in the VM here, we're able to model coroutines, which let us have a lot of these in flight at any given time, with full control flow and state and all that kind of stuff preserved. And so now the same thing with rectangles. So kind of again, we're starting with getting to HLO as kind of our core ingestion. And the first thing we do is we want to split the work as we're kind of going through it into the scheduling domain and the execution domain. And the execution domain usually just means the dense math ops. So this is in the HLO set. It's like add and mul and dot and convolution and things like that. And the scheduling ops are things like transfers. So that might be gather or scatter update or something like that. And for the actual executable blobs that we extract from that, that's where, again, we invoke the MLIR system. So in this example, it's like, well, if we were going to both SPIR-V and x86 executable, we might invoke MLIR twice with the two different backends to take that executable blob and get it down to its target form. Again, the beautiful thing is we're just reusing the MLIR ecosystem here, so kind of anything that can plug in and take the ops that we've identified as executable can then lower these all the way down and go with it. There's nothing IREE specific here. It really is just kind of like a copy paste from the original input into these executable blobs. And where we spend the rest of our time and focus is really on the scheduling side. And how do we start to really extract the benefit of having these different IR representations to get us down to the point where we can execute these things. And so kind of walking through end to end, what this means is, again, we start with whatever model your input is in. So here's some examples of some TensorFlow 2.0, which has some really nice ways of defining modules with exported functions on them that have signatures that don't require tracing, that you can kind of declaratively say what you're expecting. And kind of on the bottom there, it's a model with variables and kind of the normal stuff you would expect. And once we lower that to something like HLO, so in this example, this is the MLIR snippet of the HLO dialect here. This is what IREE sees as its input. And so here we see a simple function that does some stuff with some tensors. Again, it's all value semantics at this point. The SSA values are meaningful. And what we're really looking for here, and kind of not in this example, but this can be arbitrary CFGs of branches and conditions and stuff. So that's all fully supported. We can kind of identify variables and track those across functions. Yeah, hopefully, yeah, that's it. And so the other thing that we want to do here, once we kind of have this form, is progressively walk up the scheduling hierarchy to identify the pieces of executable code, to identify the scheduling code, and then within the scheduling code, start to define those different concurrency scopes. And the goal, once we've kind of got it in this dialect and we've done all this work, is at the end of the transformation, we know very clearly which operations we're actually going to want to dispatch, the order that we want to dispatch them in, which is defined implicitly by the SSA values and the USDEF chains between them. We have identified for those things we want to dispatch kind of where they can co-locate. This is traditionally seen as like a partitioning step, but here what we're really thinking about is not necessarily the target device, but the target stream of execution. And then across those streams of execution, what is the data that actually flows between them? Which in this example up here is still SSA value semantic tensors, which is great. So again, any optimization that we have in the MLIR toolbox for CSE and DCE and folding of various types works at all of these levels within the executable code, within these streams as we're kind of dealing with the dispatches and updates, and then between the streams. And I think, yeah, so here's a more concrete example. I guess don't concentrate too much on the IR. The big thing is that there's two boxes, and this is kind of as an intermediate transform where basically we've kind of gone through and we've identified these dispatchable executable regions. And again, this is something that traditionally is seen as kind of like a fusion operation, but in our case, we don't actually care what the operations are, merely that they are executable. Because again, what we're really trying to do is separate scheduling from execution. Now, once we've isolated these kind of executable regions of, in this case, like a dot at the top for a big gem, these are the exact things that are kind of passed on to the backends for the rest of the MLIR tool chain to go process. Once we've kind of sliced these things out, we no longer touch them, which is, again, great, because as long as the backends that we're lowering to can take kind of these standard inputs, they don't need to know anything about our framework and the scheduling we're doing, and they themselves might do further refinement and partitioning on these blobs. And so the kind of ops that we've...
Hey, Ben, can you talk a little bit about how those dispatch regions are actually formed?
Yeah, so the thing that we're looking for here, there's kind of today, and then there's where we'd like to go. So today what we're looking for is kind of work that has similar shapes. And this is kind of what you do if you were doing this by hand for scheduling dispatches on a GPU. You wouldn't schedule something that needed one invocation to add a single integer along with something that needed a million invocations to perform a convolution across an entire image. And so we effectively are doing the same heuristic here, except we're also looking for the work that we can fold in, not because it's some particular pattern we recognize, but because it would be cheap to do that work at the same time. And so things that traditionally are represented as like broadcast operations or tiles or things that end up increasing your transient buffer requirements and allocations are things that we can fold into these regions and that almost become no ops. A broadcast is just an indexing operation when you lower it. And so by doing this, we're in a lot of cases dramatically reducing the amount of transient tensors required and the size of them. And if you think of then walking the whole hierarchy and basically performing the same kind of simplification of bucketing into these little regions as much as you can, what this gives us is a very narrow contract with the rest of the program. We have explicit captures for the inputs of these regions. Like in this case, we're capturing, well, probably it's elided, but probably one of these input arguments, and we're returning a tensor. What actually happens inside of here is not something now that that we, the scheduler, need to care about. Which means if there's 20 intermediate tensors or one intermediate tensor used within here, it doesn't matter to the outside. And once we put these dispatches here, which are just kind of indicating the flow, into streams, and then start to reason about streams in the same way, we only care about the stuff moving between the streams. And that's what gives us the ability to kind of perform different allocation strategies at different points of time. And yes, it's like the kind of classic thing of define a very narrow contract and exploit it. We really don't care the execution order that these go in from a scheduling perspective, so long as they're correct. And so the more that we can kind of get into this kind of nested hierarchy of regions of data dependencies and concurrency, the more we're able to kind of elide a lot of that additional work. And we found some ops and mechanisms that are useful for representing that. So this and I linked to a lot of the TableGen files again. If you're someone who's working on their own dialect, this might be useful just to see other ops besides just the stuff in core. And what we found is that doing in-dialect conversion and lowering is super useful. So a lot of these ops only exist transiently while we're within this dialect and performing our optimization. So for example, we start with these dispatch regions or reduction regions if we're thinking about reduction operators and scans and things like that. And those only exist transiently to allow us to do things like, when we're in this step, fuse these regions together as we continue refining the graph. If we end up with two regions that are next to each other that have roughly the same workload, we can fuse those together. And that's really easy to do with nested regions, and it's all kind of taken care of by MLIR. But when we want to go the next level out and start thinking about these dispatches as these kind of opaque executable blobs, it's useful to outline those and no longer have them as regions, because at that point they become black boxes and we don't particularly care what's in them. It also allows us to do things at this level where we can do things like dispatch CSE. So if you have two dispatch regions that end up being the same because they're two parts of your program that originated from the same TensorFlow ops, we can now dedupe those across the whole program. Which, when you think about these things compiling to shaders and stuff, can dramatically reduce the number of shaders you need to compile to actually run. We can also do some kind of despecialization of these. So this is something future looking that we're going to do in the same vein is a lot of these end up with the same rough structure, but slightly different constants. And again, those constants come from somewhere. They could have been hyperparameters to the original model. They could have been properties of the operations at a higher level. But what we can do when we're in this phase and we have a nice IR is basically diff IR trees of similar regions and extract those constants and dedupe them where it makes sense. So again, strategies for reducing the total number of kernels we require and the total code size of the resulting thing. Yeah, as examples, the flow.dispatch is what we end up going to after we outline regions. We have concepts here where we have variables as a first class and kind of tensor update operations as first class operations. And that's super useful here because, again, in the goal of trying to extract concurrency, we can start to identify things like variable loads and stores that don't overlap. Or entire sequences of operations that are using those variables. And just as if this was in C and you were trying to lower this down to machine code and you'd say like, oh, this is a hot variable used a lot, I'll keep that in a register. We can effectively do the same thing now. We know when a variable is loaded and used within a sequence of streams and only stored back at the end. So we don't need to do round trips into this variable that might be in a different memory space. It might have a different layout of the tensor assigned to it. And we can kind of align all of that. Again, it's super easy to see here because these are all just SSA values. And the same kind of optimizations you do in a traditional compiler, you can now apply at this level. And it starts to be where we can really start removing a lot of the work that's traditionally done at runtime for things like copy on writes and lazy tensors and things like that. So we've got a dialect now. It kind of defines these concurrency domains and kind of the flow between them. But now we have to actually start making it real. And that means instead of these value semantic tensors, we want buffers. Instead of these, regions of streams and kind of abstract dispatches, we want actual commands that we would be recording into command buffers. And the reason we want to model this here is that, again, the same benefits that we can get from looking at the IR at a higher perspective in the scheduling domain in the flow dialect, we can now get here. If we see 2 command buffer bind descriptor sets in a row, we can fold those away. If we see barriers that are kind of redundantly described, we can fold those away. We can also do things like specialization. So we have this hardware abstraction layer. We use it at runtime. It allows you to plug in Vulkan. It allows you to plug in Metal and all these different backends.
One question. You mentioned eliding redundant barriers. Where does the barriers get inserted?
Here.
So are you the one inserting the redundant barriers?
Yes. But this is the great thing about compilers is, again, the kind of thing that we've discovered is that it's really useful to think of the dialects and the conversion between them not as like a single step, but as like we in this case convert from the flow dialect describing all the concurrency into the HAL dialect, perform a whole bunch of optimizations within the HAL dialect, and then continue down from there. Which means that any of the particular work that we're doing, like transcribing a flow stream with a bunch of dispatches to a command buffer with a bunch of barriers and dispatch calls and buffer bindings, we can write that as simply as you would imagine, and then allow other MLIR infrastructure, like folders that we wrote, to take care of cleaning it up.
And so maybe to state this a different way is that inserting the barriers, by decomposing it this way, inserting the barriers becomes a local transformation that we know we can get correct and becomes very simple. And then eliminating them is a global transformation and not needed for correctness, but it's a pure optimization that by keeping it as a separate global analysis, it means that the lowering doesn't have to do global analysis.
Yeah, exactly. And that's what's really beautiful about having this single IR for all this, a single way to define the transformations. And being able to kind of do that whole program global analysis is what lets us do things like know when we're inside of a function that was called from another function, that previous function had already inserted a barrier for us. And again, this is stuff that a lot of runtime systems do as they try to, keep caches of state and do state diffs and all these kind of things to prevent doing extra work. Whereas we can do that at compile time in a lot of cases because we can just look at the whole program. And when we do know the target, so like, again, you can have a runtime with a pluggable C++ backend of hardware abstraction layer implementations, but if you do know your target ahead of time at compile time here, you can often elide a lot of these operations. So for example, here there's like a buffer view compute range, which kind of, if it's at runtime, depending on the device, which might have different alignment characteristics and different layout rules, if you know that at compile time, you can fold this entire operation away. And so if what you're looking at in terms of your IR is a whole bunch of these kind of operations you've compiled down that are performing these kind of, buffer offset calculations, in a great deal of cases, almost all of those fold away entirely. And so the concerns that you normally have when you're thinking about one of these systems about like, what do my reshape operations become? And, what is the size and bits of my shape of my tensor and how optimal that is really doesn't matter so much, because once we get to this level, we can completely remove shapes as a concept. Shapes just become integers, and most of them become constant. So it's kind of a really neat way to think about it. And that, again, the kind of thing you're generically requiring in traditional systems, the runtime to be responsible for, is now taken care of at compile time. And the other thing we model here that's really important for the pipelining aspect is fences and timeline semaphores, as they're called in Vulkan, which allows us this kind of squishy concurrency. So we're not as we're building these command buffers and kind of scheduling them, we're not looking for explicit completion of any particular task. We're looking for the fences to hit particular values. And this is what gets us kind of the benefits of, kind of Nagel's algorithm for TCP applied here, where if you do a whole bunch of work, only when the compiler decides to insert a flush do you have to flush, and you're not round tripping and waiting for each individual command buffer to complete, for example. It allows us to do kind of dynamic batching because we can kind of at any point yield and wait for more work to come in and continue building the buffers. And kind of like timer coalescing has been popular, I guess, for like 7 years now. We can do the same thing. So if you're in a low power mode, we can defer a lot of these things as long as possible. And in a system where we're thinking about like a dedicated edge TPU and a CPU, it means that we can queue a tremendous amount of work. And if we don't actually care when it comes back yet, because say your phone screen is off, or the application is not updating frequently enough the screen to need the result right away, we can turn the CPU off and just wait.
Can I jump in real quick? We did leave out the caveat at the beginning that while many of these things are forward-looking, and if you go look through IREE, you will not find these specific optimizations today. A lot of this is based on our previous work that is not published, and specific audio-visual models and real-time systems that it was a really crappy compiler and runtime before that is actually running real work that we've analyzed, and now we're trying to make a nice one.
Yes, yes, yeah. We ran into a cliff where it was just too hard to continue with the existing tool chains and ecosystems because they were all kind of separate. And MLIR here has really had the benefit of giving us one place to do these kind of cross-cutting things all the way down without having to bottom out at, for example, an API that doesn't allow us to do this kind of scheduling. And yeah, we found simple things of like being able to defer a single invocation of the model's time step for like a sequence to sequence model could get us 10 to 50 times reduction in the amount of memory bandwidth required for swapping in parameters to SRAM on accelerators, et cetera. The payoffs here are really nonlinear, and that's why it's kind of worth it to do all of this, I guess. And this is a lot of stuff, but really just to show in the end-to-end, we're continuing on this thing. We have an executable binary. At this point, once we've lowered to this HAL dialect, we've decided we're targeting SPIR-V and Vulkan, for example. So our executable was compiled to SPIR-V. And again, using the MLIR infrastructure, so that little blob inside of there, that SPV module is the SPIR-V dialect. And the scheduling code that was before this SSA form flow dialect has now become what looks like, if you squint, the same exact code you would write if you were trying to write this in C++ to schedule that work. Only now we've been able to generate that with a very high fidelity of information that, again, normally just is not available if you're doing this as kind of generic C++ code. And really what we tried to model here is basically the Vulkan API. Again, because that's kind of immediately transferable to things like Metal and DirectVE, as well as CPU side systems. The other nice thing about this API is one of the things we're really interested in is being able to make use of things like persistent kernels and indirect command buffers to actually have the accelerators schedule their own work. So the kind of hardware abstraction layer we picked here was one that if we were running the scheduler itself in a kernel on the GPU, for example, we could have the GPU feed itself. So it's a very carefully curated set to allow us to do those kind of things. It just happens to also be basically the one-to-one mapping to Vulkan. And the kind of, by being able to do this modeling of the entire system, again, those kind of caches and LRUs and things that are normally left up to runtimes, we can elide entirely. If you want to cache a given executable, because you're going to be running it a lot, you literally write the IR to cache the executable, you define a variable to store that, and you can load it from that. There's no need for hashing descriptor sets and kind of all the normal stuff that comes up when you're trying to use these APIs and not do redundant work. And so finally, we have this VM dialect, which is just a virtual machine, so it can do basic math. It kind of lowers from standard ops, std.add and std.mul and things like that. And this is what a lot of our shape math and math kind of computing buffers and control flow and everything ends up as. And the real goal here was to, again, provide a restricted subset of the IR before we go to LVMIR and kind of have an uninspectable kind of soup of possible memory operations and stuff. Here we know exactly what we can do, and we can lower that to things like SPIR-V for running persistent kernels on the GPU. We can very trivially lower this itself to C. So if you're targeting an embedded device where you don't necessarily have a one hop to it, you need to go through some gnarly old forked GCC version, you can do that. And then again, we're kind of focusing on enabling things like coroutines, which if you were to lower this with coroutine support to LVMIR, you might use some of the coroutine support that's been getting added there recently. But that's what allows us to do the kind of deferred execution and delayed batching work. And finally, this kind of completing the end-to-end at this level, this is an example of the VMIR. The executable that was the SPIR-V blob has now become a global variable at the top there that we cache on demand. The scheduling code that was calling out to these how functions now just becomes calls to external functions that's performing the how work. And this is runnable. So in our little VM, in under 1,000 lines of code, we can actually run this in almost its complete form, which gives us that flexible deployment story of being able to deploy non-executable code to devices. And the great thing about this is none of this is the actual execution. So though we have this little interpreter for this little VM, the only thing we're actually running in it is these relatively few scheduling calls compared to the execution that dwarfs this. And so even if this is interpreted, a majority of the time is still spent on the execution we're queuing up. So it generally is fine. And kind of, we were asked to kind of give our impression of MLIR so far, and it's awesome. So like I said, and Stella said, we tried to do this before. We had a lot of good ideas and we just couldn't do them. And MLIR has kind of been the rays of sun coming down from the sky that kind of has allowed us to, as fast as we can code, basically get this stuff implemented, which is really cool. And it really is not a lot of code. Again, relying on the various MLIR backends to get us to the various targets.
Caveat, it's not a lot of bin code.
Yeah, the rest of us feel like it's.
But there's also things like this has been the great part about working so closely with the MLIR kind of core group, and we're excited to see as more people start coming into this. We joke here that a lot of what we developed as kind of we were going through last year was good examples of how not to do something and how the core could be improved to make that better. And it's been really fun to watch that happen. It feels like over time we've been finding less and less we actually need to do because the core is getting so robust. And robust in such a way that we're out of tree in our own independent repository, and we're still able to get a lot of those benefits without having to be in MLIR core itself.
I'd also jump in here too, since we're running out of time, and say that if you watched this presentation and said, well, that's great or a terrible idea, but not my target, do think about the critical things you'll want to go to are the table gen links that we put in there. As we kind of co-evolved with MLIR a bit and kind of learned to use it through multiple iterations, and that learning process was costly. And a lot of that is memorialized in the actual dialects that we built and the choices we made and the type systems and so on. So as a source of inspiration or examples, it's probably useful for the community just to know that that's there.
Yeah, when we were starting a lot of this, there was no answer to like, what is a dialect or what is an op? And so we've kind of evolved our thinking with that, with MLIR as the framework, and feel free to take inspiration from it. It's been fun, and it's a really fun system to work in. So
we recently actually threw out like the older generation of our like first draft, like first version of this, and like everything in that directory is actually like pretty new code that we think follows like very modern conventions.
Yes.
Modern as in like the last 4 months instead of the 4 months before that.
Yeah. So it's all moving fast. So yeah, we're open source. We're again trying to solve this kind of end to end. MLR is awesome.
Yeah.
Feel free to get in touch if you have questions. Like especially like Stella sits on the discourse or Discord, whatever it is.
Both of them.
One of the new mechanisms.
We should all be on the discourse list.
Yes. So happy to answer questions, even if it's just about MLIR itself, like nothing IREE specific. So yeah, thank you for your time.
Thanks. I don't know if you have questions from the audience on the chat, or feel free to unmute yourself also, folks online, if you have questions. We only have 2 minutes left, but.
Yeah, I had a question on the chat, but it's not urgent, no problem.
Yeah, feel free to shoot me a mail or file an issue. Or
Dynamic batching. Someone has a question about dynamic batching. Could you expand on dynamic batching?
Yeah, so the thing I would recommend searching for is
Can't believe I have to.
this paper on cellular batching, which unfortunately came out after we had been playing for a while with our stuff, but it's great because now there's a really nice paper and I didn't have to write something. So I recommend looking at that, which is about doing this kind of runtime batching for sequence-to-sequence RNN models. And we're basically taking the same approach where we're using on the compiler side our ability to kind of identify where we would want to do this batching, which heuristically is usually around like big gems. Because the worst thing you can do is a gem V and kind of very narrow. And so what we want to do is kind of get as much arithmetic density in the gems that we do have to perform. And the cellular batching technique is basically designed to do that.
And specifically, not even arithmetic density, but a lot of times even just coalescing things and sequencing them the right way will produce memory bandwidth savings across the memory hierarchy. So there's a lot of things we call batching that are not the classic term of batching.
That's true, especially in the case of sequence-to-sequence models or models with dependencies, any kind of LSTM. In a lot of cases, you can't batch those in a traditional way because there's the dependency. But if what you're trying to optimize is how many times you're flushing your cache, being able to execute 2 time steps of layer 0 instead, and then 2 time steps of layer 1 is totally fine from a data dependency perspective, and now has halved the number of cache invalidations that you otherwise would have got if you were swapping out all the parameters for those. And that, if I had to say there's one reason for doing all of this, that is probably the biggest reason. It just requires a lot of work.
And also not done in the current.
Yes.
We did it in our previous work, but it showed the benefit.
Yep. Cool.
All right.
Thank you very much.
Thank you.
Thank you. Bye.
Uh,
Stop recording.